One of the biggest differences between humanity and animals is that we are tool makers. For every job we do, for every task we have, we design, we build, we optimize a specific tool, whether that's a screwdriver for screwing screws, an automatic defibrillator for bringing dead people back to life, or any of the range of blades we use for everything from sushi through to navigating the jungle. We make a tool for it. And yet, I'm willing to bet that the most popular tool in the room right now is one of these. It's a multi-tool. It's not particularly optimized for anything. It's not especially the best in class. But it's one convenient package that fits right in your pocket and has enough of everything that you need that this is the tool that you carry around. It is the most powerful tool. And you find we do the same thing with software. The software we build and use looks a lot like a set of individual tools, highly optimized for a specific purpose. Searching files, modifying files, compressing, decompressing, encrypting, decrypting, uploading, downloading, and yet the tool that we pick up most often, the tool that we love the most, tends to be a tool more like Python that does all of these things. It's not optimized for any particular one, but it has everything in one convenient package. It is the multi-tool. And that's great for us. And it's terrible for security. Most of our security systems work on the level of tools. Tools are their atomic element because they're mostly run as processes, and we can handle those. We can see when they start, we can see when they stop, we can prevent them from starting, we can force them to stop, and we can see what they were told to do. But when you have a multi-tool like Python, you can't necessarily see inside of that. Living off the land is a phrase that you'll hear in information security quite often. It refers to this idea that when an attacker gets into your machine, they can't always bring their own tools with them. And so they're going to use what's already there. Anything that you've deployed onto your machines or that has part of the operating system is available for their use because you need it. And so if you're using a tool to download files off the internet, then they can also use that. The way to avoid this is to simply not deploy them. Don't leave your tools laying around if they're not needed. This is about minimizing attack surface. This means that when someone gets into your machine, they can only do a very limited set of things, and you control what that is, and you're aware of what that is. Which raises the question, is Python necessary in your production system? It is the most powerful tool. If it's there, what if it's used for an attack? What if you say, yes, now Python is essential, it must be deployed because we're using it, and then you get hacked. And you find out because your customer database shows up on the internet, and the review goes through and finds out that the attackers used Python that was already on your machine and got it out, and you had no idea. Why would you? You're tracking processes. Python started. That's the idea. That's why we put it there. We want to use it. You're looking at network connections. And there's nothing suspicious. They got in through a developer machine. They access it all the time. Why would you notice it? When abnormal use looks normal, your only choice is to watch everything. Let me say that again. When abnormal use looks like normal use, you have to watch everything. You have to track everything that happens on your production machine. You have to track everything on any machine connected to it, any machine connected to that, and put it all in one place, and you build this massive, massive haystack, and you're going to go search for a needle. And if that sounds impossible, you're right, it is. So we take a slightly different approach. Let me reframe how a lot of us will think about security. It's a very easy idea. Imagine you have your high-value, whatever it is, high-value machines, high-value database, high-value software, and you build a wall around it. That keeps the attackers out. And that's largely how we think about software security, network security, is we have a wall to defend. And if an attacker gets through that wall, if they breach that wall, then they win and we lose. And now the problem with this point of view is that you can't defend that entire wall. That wall is millions and millions and millions of individual points where an attacker can get through, and they only have to get lucky once. And they will. So the mindset that we try and switch to in more modern information security is known as assume breach. We assume that they're going to get in. And for the most part, this is a good assumption. They already have. If you have an interesting system at all, there's probably some kind of attack already going on inside that you don't know about yet. By making this assumption, we design things differently. We build systems differently because we're not just trying to detect a breach at the wall. We want to detect any motion going on inside the system that doesn't look normal. And so you build a bigger and bigger haystack of everything, but you're not just looking for the initial intrusion anymore. You're looking for any use of your software that doesn't look like your application. You're essentially putting motion detectors inside your office, even though the front door is closed. And this is why Python is dangerous, because those motion detectors are looking at tools. And Python is a multi-tool that can do everything. So when you see Python being used, you don't actually know what it's done. It's kind of like if someone borrows your screwdriver, goes away for an hour, and then comes back. You've got a pretty good idea what they've done with it. They've either tightened something or loosened something. If someone borrows your multi-tool, comes back an hour later, what have they done? You have no idea. Maybe they've cut something, maybe they've, what can you do with this? Eaten something, maybe they've trimmed their toenails in Starbucks with it. You don't know what they've been up to. And Python is just like that. Here's an example command that you might see logged in kind of a broad security system. This is one tool. We're starting a process here. But you can see everything that it's doing. We know that curl downloads stuff. We know that's a URL. We can kind of see what's there, and we know where it's being put. And we can make a decision about whether this is good or bad. What is this one doing? This is a legitimate Python invocation. This command will do something. I know what it does. It will go to the internet, and it will download more code, and it will decrypt that code and execute that code. And it's not actually going to start uploading stuff because I'm worried that people will take this and actually run it, so it just prints a hello message. But looking at the logs, you couldn't know what this does. You can't make a value judgment based on what this does because you don't know what it does. This is a totally likely command that you may see. This is lateral traversal. This is a machine picking up a program, arbitrary code on another machine within your network. So there's no random network connections here. You may not see this, but it is running arbitrary code on your machine. And maybe this is how they get in the first place, because most tools are not going to squiggle a misspelt package name for you. But this is downloading arbitrary code off the internet and running it inside Python, and you don't know what it did. This is why Python is dangerous. This is why you should not put Python on your systems. But Python's essential. Python is what all of your code is running on. It's what your algorithms are written in. It's the flexibility that's gotten you to market so quickly. It's the maintainability that lets you make changes reliably and trust that they're going to be OK. It's the reason you can hire so easily from one of the biggest and fastest growing pools of talent in the world right now. Python is core to your business. It's core to your success. And so you can't just disable it. Disabling Python is not an option. But it doesn't have to be. Despite the security concerns, imagine we have the same setup where we're collecting all of these events, we're collecting all of the tools that start, but instead of being a black box like Python is, instead of having a secret life that you know nothing about, imagine it was telling you. Imagine if every tool built into Python, built into that multi-tool, was individually telling you what it was doing as it was doing it, and giving you that ability to treat the multi-tool as a box of independent tools instead. Imagine Python was your early warning system. An attacker using Python is going to be doing things with it that you don't normally do. So when they come in and they run, you'll see in the logs that Python started. Great. It was started thousands of times, you don't even notice. But if we can see the individual things it's doing, if we can see the remote hosts it's connecting to, the files it's accessing, the commands it's running, that's going to trigger red flags. Because those don't look a thing like our application. How could you miss it? You may not necessarily act on that, but you know about it. Assume breach means you don't lose when the attacker gets in. It means you win whenever you discover them, because then you can respond. And this is where Python 3.8 comes in, because in Python 3.8, we added that way to get the information out. The feature is called auditing hooks. And it's a fairly low-level feature in Python 3.8. It's intended for the people who are managing your system, managing your deployment, to be able to say, yes, we can deploy Python. Imagine if every time C types is used, it would tell you what commands is being run, what modules are being loaded. Socket is going to tell you every IP address it connects to. That's what this provides, and it looks like this. We have a hook, which is a callback function. The arguments it takes are the name of the event and the arguments. Very much like running a command at the command line. It's going to give us that same information. This is the simplest hook I could possibly write while still using an F string, but yours is more likely going to send that event somewhere else so that you can collect it centrally with everything else. Adding the hook to enable it goes through a function in the sys module, add audit hook. You can only add them, you can't remove them. You can add as many as you like and they'll all get called, but that's it. You don't have to do any additional work at that point. You don't have to go through and enable them. There's a whole lot of points in the standard library where they're already being enabled. But if you own a third-party module, if you own something that is not CPython, that has low-level operations, it's possible to raise that event as well. Django, for example, probably a less applicable example here than other places I've given this talk, has SQL generation. It'll generate SQL code from its object model and send that to the database. With a single line change, you can expose all of that through an auditing hook and enable your security monitoring software to recognize that that's going on. And maybe that's not going to identify anything bad straight away, but the aim is to identify anything unusual. And that gives you the additional information and context to see what's going on. Now, if we're doing this for security, putting it in Python code is not really ideal because it has to run as part of the program. Turns out when you go to the people who write malicious software and say, hey, can you add an audit hook at the start of it so I can see everything you're doing? They just say no. And so we need a better solution. This may be the first time we've seen some C code on the screen at this conference, and I do not apologize for that. So CPython is written in C. And you can also add an audit hook in native code. So again, it's a callback. Simplest possible callback. We take the event name just as a string because it's always guaranteed to be a string. The arguments as a tuple. And we add the hook in much the same way. The important difference here is this file is in fact the entire python.exe implementation, or alternatively the Python entry point on other platforms. And all of the runtime is in a separate library. So you can recompile this on essentially any system and replace your python.exe with one that will always add the audit hook, no matter how it started, no matter what configuration is set up, it will always be collecting events and information, which means that no matter how someone gets onto your system, if they start running Python, you will know about it. And also importantly, we can add this hook before Python even starts. That PyBytes main function is where Python starts. And by adding the hook before that, we collect every piece of information. If you add it in Python code, you'll miss a whole lot of startup. We have one additional hook as well, which is only available in C code. It's called the open code hook. Most operating systems have a concept of loading a file that contains executable data is not the same thing as opening a file that just has plain old data. And so it has additional security for like running binaries and loading executable modules. Python doesn't have that. All the files are just files. And the ones that have code don't normally get treated any differently. What the open code hook lets us do is intercept that when it's a code file and do additional work. In the very simple case, we'll extract the path and we'll open it as we normally would. Verify it in some form. I have an example of this later on. But that verification may be, does the content match what I expect? Does the hash of the content match what I expect? Does it have some marker? There's a lot of things you could do at this point because you have the contents of the file. Whereas an audit hook, you don't have the contents of the file. The difference between an audit hook and this is we return a value. We return the file ready to read, or maybe we've read it and transformed it and returned something different in memory. It's more options. This is primarily to help avoid timing attacks, which would otherwise appear if you were only looking at the audit events. So here are the APIs. We have 6 APIs. Sorry. 2 for adding audit hooks, 2 for sending audit events, and 2 for handling the open code. And these help ensure that Python no longer keeps any secrets. By integrating Python into your security infrastructure, whatever that is, using these hooks, you will see everything that it's doing, and as necessary, you can influence what it's doing in the same way as if each tool was individually controllable. So I've been very abstract. Let's get to some concrete examples. So I have 3 examples for 3 primary scenarios that you would care about. The first is enabling known good code. Because this is a controlled deployment system, you know what code you've put out there, and you only want to enable that code to run. This can obviously be bypassed in certain ways because that's what an attacker is going to try to do, and we assume that they will succeed at some point. So the second scenario is blocking known bad code. In essence, a malware scanner is essentially this. That's what my example will be when I get to that. The third scenario is log everything. That's the most important one. You can try and block things. That's a very aggressive move against your own developers. And if you block things incorrectly, you will lose developers. And if you don't block enough things, you will be attacked. But if you log everything, you will know that you've been attacked. And that's the important thing. My 3 examples are going to be based on the Windows services that you would use when implementing this on Windows. It's possible to implement all of these on other platforms as well, though a little bit more work. Windows has the nice factor that there's one obvious way to do each one, and they're all fairly straightforward integrations. So I'm going to go with those examples. If you are interested in other platforms, feel free to come chat to me later. Most critically, if you own another platform and are responsible for providing Python on that platform, I would love to talk to you because you're probably the best person to provide these kind of connectors for your systems. So, allowing trusted code. And the service we use for this on Windows is called Windows Defender Application Control. The basic concept is that the operating system owns the configuration. By default, nothing is allowed to run. And you have a big configuration file that says the things that are allowed to run. The OS manages all of that. If you're interested in how it keeps that secure, come and chat to me afterwards. It is fairly impressive, but I'm not going to go through it in detail right now. The important thing is the operating system handles that configuration, and it can be queried for a certain file. But it starts by blocking everything, and it blocks everything in a nice interactive way, where your application is just not allowed to run. By default, this works for executable files or things that the kernel knows it's executing. It doesn't work on plain old Python files. And so with this integration, we're going to use the open code hook to enable the same configuration to apply to Python source files. So that if you're on one of these properly configured machines, you can run your code if you've enabled it through the configuration, through the policy. Otherwise, it will be blocked. Configuration is XML. This is about 0.1% of an actual configuration file. They are extensive. There are also some really good tools for automatically generating it, and the general advice is set up a machine that you know is still safe and run a scan tool that will look at everything that you use on it and generate it for you from that. But I want to give some examples of the kinds of rules. You have file-based rules, which are going to allow or deny specific files based on various metadata, either the file name, the full file path, if you know exactly where it will be on the system, the hash of the file. You can also use publisher information, version information to allow and deny certain programs from being run. The more interesting one is you can also specify signing certificates. So Windows has an integrated code signing architecture where certificates can be marked as trusted, and any code that's been signed with that certificate will be allowed to run. And this is how we do this here. This certificate is the Python Software Foundation certificate. It's the one used to sign all the Python releases for Windows, or the official ones. And so by enabling it in here, we enable the Python Software Foundation version of Python. And that includes, so .py files are not directly signable, but you can sign a catalog file that references all of them, and Windows knows how to verify that. So we haven't actually done a huge amount of configuration outside of this to make it work. But the important part is the integration in the open code hook. This is a helper function that's going to implement most of the check. So the verify file descriptor we saw earlier, this is that helper function. It's going to take in the file name and an open handle for that, which that and the parameter extraction we're not going to see for this one. We stuff it into the structure that we need for the call, but then we make one call into the operating system and say, what is the policy for this file? The OS is going to look at that big configuration file and say, this .py file with this hash is allowed, is not allowed, whatever. If it comes back and says it's not allowed, we should enforce lockdown against this file. Then we'll bail out and say this file is blocked, don't run it, otherwise it's allowed, and it's okay. This is the integration. This is fairly straightforward. The idea is to put as much logic centralized because you're going to be using it for your entire system. This is not so much a Python logging system as the ability to integrate Python into the systems you already have. And so a connector should be fairly straightforward. What this looks like when you run it. My first example is importing the collections module. So this is in the Python standard library. It comes with a signed signature in the catalog file, and so it's allowed when I import it. Now I modify the random module so it doesn't match that signature anymore. And when I go to load it, it's blocked by policy, which is the fancy way of saying Windows Defender Application Control blocked this, it's not allowed on this machine. What this enables is about as integrated a way as we have to restrict a machine to only run the things it's meant to have. Anything new arrives, it cannot be executed. But as I said, the attackers are smart. They only have to find one way through it. And when they do that, we still want to have a way to stop them. Deploying the configuration is a big task. And so when we have something known bad come up, when we know that we're infected, we know that there's malware automatically replicating itself to every single machine, and we want to shut that down, but we know what it looks like, we want a way to roll out some kind of signature that says, if you see this file, don't allow it, which is another big step to get through. On Windows, we can use the anti-malware scan interface for this. This is a central operating system API that lets arbitrary programs talk to whatever malware scanner is enabled. So it's not tied to any particular product, and it doesn't even necessarily tell you that there's a product on the other end when you call it, but it's a way to say, here is some code, or here is a file that I'm about to execute. Do you think this is okay or not? And it will give you essentially a yes-no answer. For this one, we'll use the compile hook, which I'll show you on the next slide, but here is the helper function for verifying it. Again, it's a single function call, AMC scan buffer, and we're passing in the code, which we've got because someone's trying to compile this code, and the file name. The file name is mostly for reporting purposes because if this detects something, it's going to set off alarm bells, and it has to be able to tell you which thing is got the alarm. And if the result says this is malware, then we say, OK, the file is blocked. Again, fairly straightforward integration into an existing service that we're using for everything else. The hook around this is the compile event. So we're going to check if this is the event. And if it is, then we'll extract the parameters. The parameters are fixed for every event, so you don't have to worry about the contents of this changing. Though I will say for this example, I've abbreviated it slightly. There's a couple of edge cases to worry about with compile. And then we call the scan function, or our helper for that function. And if it says the file is blocked, we raise an exception, and we don't go any further. When you run this, this gets fairly interesting. So I have to call a function to get a test string. The reason I have to do this is because the string is encrypted in that file. The reason the string is encrypted in that file is because if I just have actual malware in a test file, then the malware scanner is not going to let me run the test because it's going to detect it and say this file is blocked before I've even gotten as far as running it because they're all watching the file system already. But because it's encrypted in the file system, it doesn't see it at first. Then when I decrypt it in memory, it has no actual way of finding it until I take that string and I eval it. And when I pass it to eval, that's going to compile the code, which will trigger the compile event, which will trigger the malware scan, which is going to report that it's malware because that's what that string means. And we're going to block compilation because of that. We're also going to get this little pop-up because that's what our malware scanner does. I ran this locally. If you're running this set up in a network, you'll get a distributed event. It's going to fire everywhere. Your administrator is going to know. I'm probably having my machine investigated right now for the amount of malware triggers that showed up when I was testing this because they get sent to the administrator. That's the whole idea. You need to know what's going on in your system. This is a great way to find out. But the really cool thing about malware scanners is they are designed to take updates frequently and independently. So once this was deployed, when new malware is found, that shows up as a signature update, which does not require redeploying the entire system. And in fact, they largely happen every hour or two if you're on the fastest path. But it doesn't require shutting down your system. It's designed to be able to apply the new signature without shutting everything down. It's not a deployment step. It's not even a configuration change. And so, for example, when we had the big ransomware spreads going on a couple of years back, Petya, NotPetya, WannaCry, all of those, they were largely shut down because we got the signatures out to the malware scanners. And whether you're installing operating system updates or not, you're getting those signature updates. And once we had the signatures in, they were just blocked, and they were not allowed to run. And that's largely how the spread is stopped of these things. You get them through a malware scanner that is not deploying updates. It's not forcing you to reboot or anything along those lines. And so now we can integrate that with Python for handling encrypted code or in-memory code. The third scenario is log everything. Everything. Just log it. You need that information because the most important thing, as I've said a few times, is not preventing the attacker from getting in as much as it is knowing that they're in. Because once you know they're in, once you know what they're doing, you can formulate a directed response plan. But as long as you're trying to defend 10 million entry points, there's no way you'll be able to cover them all off. But the engineers in the room are all going, if I log everything, that's going to be really slow. And yes, it is. For an individual request or task, if you add lots and lots of logging, it's going to be a little bit slower. On the other hand, if an attacker gets in and steals your customer database and publishes it on the internet, and your company has to pay a GDPR violation, and you get shut down because you go bankrupt, your website is going to be a whole lot slower than if you had the logging in, and you may be optimizing for the wrong scenario. The good news is, all the logging infrastructure that you would have access to is designed to deal with this problem. It's all higher performance than anything you're going to roll yourself, and the Windows event log is included in this, and we'll see why. But the primary reason is deferred formatting. So to write to the Windows event log, you define all of the events that you're going to do. It's more XML. Here's the interesting part. We have a template here. So any event is going to have a certain amount of data that has to be included, and here's where we define that. So we can say up front, this takes 2 strings. We give them names, and by saying the int type is ANSI string, that really just means const jar star. It's an 8-bit string. And when we log the event, all that's going to happen is that will be copied and stored somewhere. It's really efficient. The formatting message doesn't get used until much later on. When someone actually goes to read that event, that's where this string gets loaded. They do the formatting. They'll use that UTF-8 marker to say when we read this text, treat it as UTF-8. But compared to, say, a print statement, where you're doing all the formatting up front, you're doing all the string conversion up front, this is going to have much less impact on your code as it's running. And the substitutions occur later as well. So it's the deferred formatting for these 2 fields that provides a lot of the performance improvement. When we run this huge XML file through the standard tool, it gets converted into 2 things. The first is actual code that you can use to raise the event. So it's a header file, it's a C header file that you can import and call. That will raise the event, which makes it very simple to connect into the event log. And the other half is a file that contains all of the messages. So that message string doesn't even end up in your program. And so when you go to view the events, it looks like this. We have a Python operational log. Operational is the term that we use here to just say things that we expect, normal operation. You could have a separate one for security events or errors or fatal events, whatever would make sense for your particular context based on what you're collecting. And an event, as I said, gets formatted later, so you can see the contents here has been formatted with that string. And we have the file name included, and if you're familiar with the contents of the Python standard library, you'll recognize that that's the actual code from that file. It's been logged, it's been collected. And this all gets done in our compile event again. So the compile event gets raised not just when someone calls exec or eval, it gets called for every single file that gets imported from Python source. So it's one nice central point where every single bit of code that gets executed can be collected and can be reviewed for whatever you want to do. In this case, if it's not the compile event, we'll bail out. We extract the code as before, and we call that generated function to simply just say log this data. So there's no formatting, there's no text of the message here. This is 2 string copies, and then we're done. And minimal overhead for the logging. And so with minimal overhead, yes, you should just log everything. But to add on to that, the caveat to that is remember that everything you log, you also have to read. And so I really want to emphasize you should enable what makes sense. Because if you don't have the people who are willing to wade through all of these events, or you don't have the people who are willing to apply anomaly detection or machine learning to these events to identify things that stand out, then there's very little point enabling everything. This is not simply a case where collection is enough. Collection is the start of the process. You can build a huge data set, and as we know, that's great, but you actually have to do something with that data set to get any use out of it. Knowing your opponent is so important, because I guarantee that most of you don't actually know who your opponent is. Because we mostly think that we're the good guys and we don't have opponents, people who are working against us. If you're running anything in the cloud, you're a target, because the real target might be someone in the same data center as you, and an attacker is going to go through your machine to get to them. And sure, they don't know you, they don't hate you, but they're still going to use you, and you'll be breached as part of that. Or maybe your opponent is not even an actual person. It's generally considered now that the NotPetya malware from a few years back was a targeted attack against a couple of Ukrainian companies. And yet within 24 hours, it spread around the entire world. Because people were vulnerable, because they weren't prepared for that kind of entrance into their system. Auditing hooks in Python 3.8 allow you to take control. Security in Python is no longer a case of simply remove it because that's all we can do. It's not a case of let's wait for the open source developers to figure it out because they're never going to do, we, myself included, are never going to do exactly what you need. The choice is not between getting rid of Python. The choice now is, are your tools going to serve you and your users and empower your attackers? Or are they going to act as an early warning system? Python 3.8 can be your early warning system. Make your attackers wave their own red flag when they get into your system. And let your security teams know that it's time for you to upgrade. Thank you.